stage. Okay, thank you, Steve. Recently, I've done a small project with a biologist from Stanford going through some large life sciences data sets. And because of that experience, I have some material here that I can show you today to show how we with AllegroGraph work with life science data sets. Now, so the whole point of this seminar is I will assume that you work in the life sciences, and I will show you a little bit how you use AllegroGraph. Okay. I also will assume that you know about RDF, so I won't go too much in detail about that. In my talk, I will spend 2 minutes about explaining what AllegroGraph is. Then I will first dive into a really large non-biological data set with 1.1 billion triples. It's called the Lubum data set. I will use this to explain Graph and AllegroWebView a little bit, and then I will dive into the Science Commons data sets, and again use Graph and AllegroWebView to navigate through the data and do Sparkle and Prolog queries. And then, because I did this little project with this biologist, I will give you some of my observations of what I see when someone works with data sets, and I will talk a little bit about when to use Prolog or when to use Sparkle. Okay, so again, I do assume everyone knows RDF. So AllegroGraph is an RDF triple store. So with an RDF triple store, you basically open a store, and now you can say whatever you want to say. So I created triple store seminar.db in Python in this case, and I would add some triples, like there's a person with the first name Steve who is an organizer and 52. There's a person Jans who's a psychologist and 50. There's a person Craig in this room who is a salesperson and 32. And then I can do one-to-many relationships directly, so I can say that a person 1 would be a colleague of person 2 and of person 3, or just for fun that person 3 is a neighbor of person 1 and person 2. And because I can say whatever I want to say in a RDF triple store, I will say person 1 likes a pizza, and then this is how it looks like in Graph, our visual interface to the triple store. And you see why we call this a graph database, because what you see is a graph. And we allow people to do both Prolog queries and Sparkle queries on our data sets. So here's, for example, the same query. X has a colleague Y, where Y is a neighbor of X, and then X is a first name, and Y is a first name Y name, and you will get these results back. And here's the identical query in Sparkle. So AllegroGraph is a scalable and persistent triple store. We load and query over billions of triples, and we're the only fast reasoner that doesn't need any materializing. We recently, for 3.2, added a query optimizer. And what we now see, if you look at these data, is that if you compare us to other triple store vendors, that we're in the same range for doing fast queries with reasoning. The top picture shows you, well, this is about the Lubum 8000 benchmark. Lubum is it's the Lehigh University benchmark. It is an ontology of what a university is, what kind of people work in a university, kinds of professors, kinds of students, types of publications, types of sub-organizations, etc., etc. And then there's a list of 14 queries. And here you see the times for the big queries, and below you see the times for the really short queries. AllegroGraph is doing, is fast, most queries faster. But that's not so much important. What's more important is with our database you can load data, index data, and then from that point on you can do your queries instantly without doing any type materialization first. Then we are compliant with all the standards: RDF, RDFS, OWL, Sparkle, named graphs, ISO Prolog. And then we have a reasoner, an RDFS++ reasoner, so we don't do full OWL, but we do everything in RDFS, and then some of these OWL predicates, so same as, transitive property, inverse of, and has value. We do full text indexing, and then, and we won't talk about it today, but we also have libraries for spatial, temporal, and social networking. So first let's go into to give you a little bit of an idea how our tools work. I will start with going to a tool called Graph. And Graph is a tool that lets you do Sparkle queries, Prolog queries against the database, but it also visualizes results. And you can both look at the graph view and a tabular view. So let me just demonstrate that. So I have the biology database already open, so let me go to Lubum 8000.
You might want to mention the delay that doing this over GoToMeeting can happen into the visualization.
Oh yeah, so I am, yeah, there will be a lot of screen changes because it's a visual interface. So for people on really slow connections are a little bit out of luck today. Steve, please help me to do this all as slow as possible. Okay. So at the I had already a triple store open, so I'll close the current triple store, and then I open the file Lubum 8000 on my machine, and I will open it in read-only mode. Then I have to wait a few seconds, it's 1.1 billion triples, to set up all the internal tables. And it's opened, if you see at the top, so now you see that the triple store well, it's opened, it's of course not in memory, it's 1.1 billion triples. So let's start by doing a simple query on this data set. Let me see Sparkle, and I take a Sparkle query. Sparkle query. I open it. So this is the Sparkle query. Okay, well here I've got my students where I say there's a student that takes this particular course, and this student is of type graduate student. I get a list of students back. I create a visual graph from the results, and here you see how all these students are related. So I can look at a particular student, and I can say, I can hit the T button, and I will see that this particular graduate student 124 has an advisor, an email address, is a member of something, has a name, takes a bunch of courses. So let's look at a particular course. This course has a name, has a type graduate course, and there's a student, and of course there's a professor for this course, and this professor is the advisor, say, of a whole bunch of students, and has some publications. So I can go back to the graph view, and now I see that I added some of these. I can take a step back. So here I am. Let's do the Sparkle query again and say let's look at graduate course 1, and I can do query again. I get some other students. Let's select student 117 on the left, and I go to the graph again, and so I have the student here. Now what I want to do is I want to find a link between, say, this student and any student here. So I can say and I say I want to basically look at subclass relations, teacher of, teaching assistant of, publication author, and I want to follow these links in both directions. So I say OK, and then what I can do, for example, is I can hit Shift F. Well, first let me put this guy here, and I pin it down so it won't change when I find a link between students, and I do a Shift F to get from this student to, say, a course or a professor. Let's take this person here, and then what we see is after a while we get the link between the graduate student and the student that I was initially following. Right now we get too many links between these students, so I will go back one step, and I will say I only want to see the links between this guy and this guy here. So I can also just do Ctrl V and look at this, and then I didn't link this guy, so let me pin this guy, and let me take this person here and pin him too. pin, and then I take this guy again, and I say Shift V, and I go there. And I find all the links between these different people. So this allows you to find relationships between entities in your database and go through, in this case, through publication author as a type of link, a teacher of link, and a teaching assistant of link, and find connections automatically. So instead of writing Sparkle queries or Prolog queries, I can do the whole thing automatically and let the database discover links. So this is for a large database. So where I can, so it's 1.1 billion triples, and when you see how the graphs are formed on the screen, it looks reasonably well and fairly snappy. So let's go back to my presentation. So about 2 years ago, some people started a project where they decided to load all the available OWL files in the life sciences and put it into one big database or several databases, and see if all these databases could somehow be correlated and if interesting things could be found in the databases. So what people did is, and this will be only relevant for the biologist in the audience, they would take these databases and load them in. So for example, there's PubMed. There's the literature would be PubMed, which is probably 13 million different articles in the life sciences, fairly well classified. The authors mostly unified. There's the Allen Brain Atlas of a mouse. There's big gene ontologies. There's a whole taxonomy of the animal kingdom, and it all went in one big database. And then in that process, people, as an example for this particular endeavor, they would try to find where on, well, in which places in a particular neuron you could have places that you would target with drugs. And so the types of queries they would do would be something like this, and this is a very hard query to read, but this is a database, that a Sparkle query that goes against at least 4 different databases. Okay, so this is the typical query that people would do against this data set. And my acquaintance from Stanford helped me with getting all these same data sets. It's about 100 million different triples, including all the text indexing for RDF comment and RDFS label. Loading this thing takes, on one CPU on my machine, takes 1.5 hours, including the text indexing, 15 minutes, sorry, for the loading, 15 minutes for the indexing, and the total time would be roughly 1 hour and 45 minutes to get everything in the database. And now let's go to this particular database. The first thing I could do is go to a browser. So let's start up a browser. And we have, so what I showed you before was graph. I will show you graph again on this data set. But first I will show another tool that we have. It's called AG WebView, which is a browser interface. And it's on an internal machine at this port. So I have 2 databases here, like in graph. I have BioOntology and Lubin 8000. Let's go to the BioOntology. And I have to wait a few seconds. So what you see here, there's 99 million triples in the store. Reasoning is enabled. There's some namespaces already defined. And let's just do a simple query. So here's a bunch of queries that I could do just for fun. Say so here's some saved queries that I can try, and let's do a simple one. Say this is a Prolog one. Select every XY, the first 10 of them, where X has RDF type Y. I type this in and I get 10 results. I can click on one of those, and then what you see is all the things that go outward from this thing. By the way, if I want to see the graph names, I click on the graph names here and I see the longer version, and here I get the shorter version. So here I have an RDF type database. The identifier is this. Oh, I want to go back. It's of type database object. Must be a whole lot of database objects. Anyway, but what you can see here is that, so now I'm probably in authors that have the name Fisher. Yeah, he has it's modified at this particular time. There are probably even other objects modified at the same time. Yeah, that's amazing. So there's a particular author that has this number. So anyway, what I'm just showing you, you're kind of going through your triples and clicking on any part of the triple that you want, and you will see all the rest of the information about the triple in your screen. So let me get back to the queries. So say I have the saved queries, and say I want to do a query like this. So I can say this one. So I say give me the first 100 triples where S is a subclass of T and T is a subclass of U, etc., etc. So there's a whole subclass. And my screen, because of GoToMeeting, is much too small, so I can't show you all the things going off to the right. But this gives you fairly quick results. And I can go back and I could, for example, say, let me take this thing here. Here you say, if something is a subclass of another thing. Now, in our triple store, we support various forms of reasoning. We do RDF subclass and subproperties. We do inverse, we do same as, we do transitive property. So all these things are supported. And when I look at this big biology database with roughly 100 million triples, what you mostly see is that people use subclasses. There's a lot of OWL in there, but it's fairly simple definitions. And what I'm doing now is I'm taking the query, I'm taking one thing out of the taxonomy in this database, and I want to know all the things that this thing is a subclass of. Now, what actually is doing is AllegroGraph is doing a little bit of real-time materialization. So for the first time when you do subclass, it will actually build up all the subclass relationships in the database, and I think it takes about 40 seconds, 50 seconds to do this. So now you see that this thing here is a subclass of roughly 21 different classes. So this is the highest class, this is the lowest class. If I can turn reasoning off, and suddenly I get only one result back. If I turn it on again, I get a whole bunch of results. Let me turn it off again and let me look at the other query that I had. So I say saved, and I take, for example, this query, let me first do this one, subclass reasoning. So here what you say is this particular element from the taxonomy a subclass of this element of the taxonomy. And if the reasoner is off, you don't get any results. If the reasoner is on, you suddenly get the result yes, because there is a subclass relationship. You turn it off again and there's no results. And then I've currently shown you only some prolog queries. I also can just as well take queries in Sparkle. So let me take this one. So I have a query where I find everything that is described by a particular gene type, that has a name, that is described by a taxon, there's an identifier, and then you have the typical filter thing, and then here you get the results for gene, name, ID, chrome, taxon, and type. And you scroll down, and everything in here is clickable, so I can click on this. I can click on this thing, and then I get all the information about well, this particular thing. I hope that makes sense. This thing allows you to make namespaces. Users have to log in. So people can have their own queries and store them. For example, if you look here and you take a particular, this one, I could say, let me go back. I can share this query with other people in my group, or I can have my own personal questions. And that's about what I wanted to show about AllegroGraph WebView. So now let's go back to Graph. So I'm going to do File, and I say I'm going to do Biology database. There's already a triple store open. Okay, so I will close it. And then I say read only for the database. So I now have it open. So now I'm in the query view. I can go to the graph view and say, let's start with one link. So I add a node. There's various ways to start. You can add a node by URI or literal. You can type in a label. If you click on this one, you get all the class hierarchies. But for this database, it will take a while because there's more than 500,000 classes and 500,000 types. So let me just do one. Say a C star, Astartoidea. So now I have one of these links here. This is just a label, and I see it's a label. So if I want to exploit this thing, I click on this thing. I say F, and now I get a class of things. So I type I again to see all the predicates for this thing, and I say, okay, let me explore everything where there's an exact synonym, a label, and a subclass of. And I'll do it in both directions for the triples. So now I could click on F, and I get the things that is the subclass of. The left-hand side, you can see what the names of the various links are. I can also push N, and I temporarily see the names of every relationship. I can toggle this on and off. Sometimes helpful. I can say, okay, well, let's explode this one a little bit, and now let's explode this one a little bit, and let's explode this one a little bit, and then maybe even explode this one a little bit. And so we started out with, I think, this thingy here, and then we went all the way to this thing here. Of course, I can say, go always back a step, go forward again. And if I want to do some automatic discovery, or if I want to know if the database can find links between elements, then just go throw away some links in between. So I think I can throw away this link. Let me throw away this link. And let me throw away this link. And so now I want to know, can I find a link between this thing here and this thing here? So try to pin this here. And I say Shift F, and I say just find a link. And what I see is I find a link from this thing to this thing. Look at the bottom where you see the full URIs for this thing. You go here, and then you go here. I can take one step back and say only look at the direct links between them, and not the rest. Don't show me the rest. I type Shift V, and I go here, and then I find that the whole link, that this thing is a subclass of this thing, and this thing is a subclass of this thing, this and this thing, and so it all gets back to this particular class of Pinaroida. Again, I hope that this makes sense. So when I showed you Lubum, I used 4 predicates to go through somehow this thing. The shortest way to get from this thing to this thing here is through the subclass relationships. Let's do some queries. So I can say, well, let's do a Sparkle query and find one and say load a query string. Bio Q1 Sparkle query. So this is a query where you say find everything about an article. find everything where there's an article that's identified by MID and then this particular number, where the thing is a journal article, and then you get this object here. This is not a very exciting query. I say load query string, and I say this is a more exciting one. Bio2 Sparkle query. I open this one, and let me temporarily make it a little bit bigger. I think I showed you this query also in the AG web view, so now I'm going to do the same query here. Say do query. It might take about 10 seconds. So here I have a whole bunch of results. I can turn this thing into official graph. So let me go back. Here you see the results. So this is what you asked for. You get them back here as results. If you want to create them in an official graph, you do it this way. And if you want to store this for later, then you can even say save the layout state and say we do a seminar demo, and I save it, and now say I clear and uncache everything. So now I have an empty screen again. It's forgotten everything about everything we did so far. Now I can say load a layout state, and I find the seminar demo layout. I open it, and here I have all the things again. And I can look at them again. And so this is a way for you to slowly build up your queries, store them in your file system, again share them with other people, and slowly get more and more interesting queries. One thing I haven't shown you that I wanted to show is that both AG WebView and Graph also support full text indexing. In Graph, we're working on having another another widget where you can just type in a series of words. So if I would do it in AG WebView, and I hope you now all see it, I could say, okay, give me all the things with, say, blood and vessel. And here you would get all the triples that have the word blood and vessel in. So what I was showing, that we do also do full text indexing in this database, which is really, really handy if you want to get the first string that you're looking for. And in AllegroGraph, it's in AG WebView, it's fairly simple. We have a search box. We don't have it yet in Graph, so we're working on that right now. If you want to do it, there's a way. One thing is you load a query string. Thing has words query. Let me see if I already defined the rule. You can say select every X has the words X, where the object for this particular X has the words liver and kidney and amino in it. And what you will see is that you get a series of results back. So this is, we need a widget, we realize that, but if you need full text search in Sparkle, in Graph, then you can have it. And of course, Sparkle already supports full text search in Sparkle queries. So that about the demo of Graph and AG WebView. So I was watching this biologist playing with the data, and I noticed a number of things while they were working with that. What I saw when I looked at the NeuroCommons datasets is that all these queries had graph expressions in them. So if you, for example, look at a query that I showed you earlier, where we were looking in this Alzheimer experiment, you would see that in this one Sparkle query there would be at least 8 references to named graphs. But because each named graph is basically the name of a file, and the URLs in these files would be unique anyway. I was wondering why you needed this graph until I realized that most triple stores partition the databases by having graphs, so it makes some sense, and it actually might sometimes make things more efficient. In AllegroGraph, we use the graphs too, but they're less important because I think that actually it's a bit of cheating that you have to insert these graphs everywhere. In an AllegroGraph database, you can or just stick everything in one database, and if you want to use the graph, that's fine, but usually you get the same results without. And we have federation, so what we can do is you can load all this data in different databases and then do your queries on top of that. And again, without using the graphs, because AllegroGraph will figure out where your triples are. So that was one observation that I had. The other one was I was looking at other triple stores where the data was, because we were kind of reverse engineering how the data sets were put together. And what you see is, for example, in this whole 99 million triples, there's 3.5 million subclass relationships. And I say here sometimes to 10 levels deep. I since then found out I found links of 21 levels deep. And if you want to do queries and you need really to find out whether one thing is a subclass of another thing, and there might be 10 steps between, then other triple stores need materialization to kind of pre-compute all these links so that if you do a query, it's at least fast. In AllegroGraph, we now have this query optimizer, and what you just saw is that the first query with the subgraphs took me about 40-50 seconds, but then every other query ever with any subgraph would be instantaneous. So we have in AllegroGraph a much faster way to do materialization. Most of the time we don't even need it. Third thing, and I didn't show you that today, but in the database, especially in the brain map of the mouse, but also in other places, there's a lot of dates and a lot of numbers with certainty factors. AllegroGraph is very efficient with those. And I guess the next time when I do this, I will get you some queries, particularly with this. And the third one is what we can do in AllegroGraph. If you look at most Sparkle queries, you will see that they're really, really long because Sparkle doesn't have a facility to make rules. Actually, Top Quadrant is working on a Sparkle rule system. Some others are too. If you can live in Prolog, then what you will see is that you can make Prolog functors, and you can say take parts of your queries and generalize a little bit, and then suddenly your queries get a lot shorter. I was giving this talk before for a group of biologists, and they wanted to know when do you use Sparkle and when do you use Prolog. And to my surprise, about half the people in my audience were using Prolog for their biology work, so that was a really pleasant surprise. But what we see is that if we look at our users, about 70% of our users use Sparkle only because, well, it's the standard query language. There's good description on the web. There's a quick growing community that can help you. And there's more and more Sparkle endpoints. So Sparkle really makes a lot of sense. But what you have to understand that Sparkle is basically an access language and not a query language as such. What we see is that 30% of our users use Prolog just because they need the probing aspect. So they use Prolog because Prolog is not limited to 2 arguments. We can do range queries. We can build rules. And we already do have a query optimizer for this. So, and I've not put this in this list, but actually if you look at the Prolog rules and the Sparkle rules, the syntactic difference is really, really small. So anyway, this is all I had to say. Thank you, and see you next time.
See you next time.